I thank you. I thank all of those who are listening. The talk is based on joint work with Yuval Perez, and the next slide will explain a little more. So, the work is not new. We did this about 20 years ago, just before Yuval left Jerusalem to Berkeley. The trigger for this work was a talk at our seminar by Zev Rudnik. He spoke about a joint paper of his with Alexandru Zaharescu on the distribution of spacings between fractional parts of lacunary sequences. It might have been some other work on his on distribution of spacings. My memory is not that good. Over the years, I've spoken about this work several times, and I apologize to those who have heard this before. I can only remind you of what I heard years ago as part of advice being given to speakers, especially to young speakers. Never underestimate the pleasure that people get in hearing things that they already know. You're probably quite familiar with this. When you go to the concert, you often enjoy more hearing a piece of music that you've heard before. In the opposite direction, I'm going to recycle what I once included in a long paper that I wrote with the late Dan Rudolph and with Matt Foreman. In explanation, we can do no better than to quote the historian of science, George Sarton. He wrote a multi-volume history of science. As far as scientific matters are concerned, I try to say enough to refresh the reader's memory, but do not attempt to provide complete explanations, which would be equally unbearable to those who know and to those who do not. Okay, so after these apologies, I'll start with the talk itself. So I assume that people know the usual notion of normality. And normality is expressed either for points in 0, 1, or for sequences of zeros and ones, which represent the point in base 2. And what it says is that the empirical distribution of the k blocks, these are a block of consecutive digits of length k, and the empirical distribution means you count how many times a k block occurs up to the nth digit, divide by n, and let n tends to infinity when k is fixed. And this should converge to 2 to the minus k, which is the Lebesgue measure of these blocks. When you think of the measure-preserving transformation of the unit interval given by multiplication by 2 mod 1, this is the usual notion of generic points in dynamics. I'll come back to that a little bit later and explain a little bit more about that. Borel, more than 100 years ago, in 1909, proved that almost every point in 0, 1 represents a normal sequence. And this was the first instance of the strong law of large numbers. Another of the basic theorems in probability is that when you take sums of independent random variables, but the probability of each of these random variables is very small, is on the order of 1 over n, then this will converge in distribution to a Poisson random variable. This is called the Poisson limit theorem. This is the theorem that you can get. You can see this if you take a random book of 500 pages and you count the number of errors on each page. Then this will, and then count how many pages had no errors, how many pages had one error, how many pages had two errors. This usually corresponds to a Poisson distribution, assuming that the book has had a reasonable proofreader. Here, the sums of the independent variables are not normalized by dividing by n. So a natural question to ask is, when you see a sequence of zeros and ones, can you generate a Poisson random variable out of this? And perhaps this can be done in several ways, but we were led to the following definition. And since everything works just as well when you deal with B digits, so we'll work with B digits. It's just so what are we going to do? We're going to take omega to the k, which are the blocks of length k consisting of digits from 0 to k to b minus 1. So the size of this probability space is b to the k, and you put the uniform probability measure, so each omega gets the mass b to the minus k. On this space, we define a random variable. After we fix a point in omega to the n, okay, so I can use the little red button or whatever, I don't know what you see. And we define the random variables m sub k super x of omega, and this just counts up to b to the k minus 1, how many times you see omega. You need a little bit more than the first b to the k digits to see this, but nonetheless, whether or not you count the last blocks is irrelevant. And we say that a point is simply Poisson-generic if in distribution these random variables converge to the standard Poisson random variable with mean 1. What this means is that we have a sequence of finite probability spaces. These are the omega k with their measures, and we've defined on them random variables depending on x. This is the m super x sub k. Convergence in distribution simply means that for all integers, the probability that mk super x is equal to j converges to 1 over j factorial e to the minus 1. In particular, when j is equal to 0, this is simply e to the minus 1, and that simply means that the proportion of k blocks in the first b to the k digits, which do not appear at all, is converging to e to the minus 1. So instead of testing all k blocks, we're doing something much more mild. We're just counting how many times blocks appear. Now, why is this interesting? The first thing that we prove is that this kind of innocent-looking convergence implies normality. It's a stronger condition than normality. And I have here an informal proof of this fact. This is going, I think, a little slower than I expected, but whatever we managed to do. Begin by showing that sequences that are simply Poisson-generic are normal. Now here's some good notation. x1 super n is the initial block of length n. Fix a d and an epsilon. You first find an m naught, such that for any m bigger than m naught, the distribution of d blocks in x naught m is within epsilon of the uniform distribution on omega d. So we're going to be checking d blocks for the normality. you apply the weak law of large numbers to find a k naught, so that for any k bigger than k naught, the set of omega in omega to the k, such that the empirical distribution of d blocks in omega is within epsilon over 10 of mu d, satisfies that this measure is 1 minus epsilon 10. So you do two things. You first find an m such that the distribution of d blocks in x naught m is close, and then you want that these d blocks occur with very high frequency. Next, you choose an L, which is going to be a cutoff. So for a standard Poisson random variable, the probability that you're bigger than L is less than epsilon over 10. The Poisson distribution decays very rapidly. It decays like 1 over L factorial, so this doesn't have to be very large. And also the cutoff for the expectation, it's the same. Now, if X is simply Poisson-generic, you find a K1 bigger than this K naught, so that the distribution of our random variable is very close to the distribution of Y. Now what happens is that when you look at any m bigger than b to the k1, when you compute the distribution of d blocks in x1m, you first choose k so that m is between b to the k and b to the k minus 1. Now the frequency of the k blocks that belong to AK was this good set which had a very high measure. And in this good set, the empirical distribution of d blocks is very good. It's easy to find a disjoint collection of these which covers the same large fraction, and you can calculate the distribution of d blocks within these good blocks to get the conclusion. So the idea is that because we know that we're covering our space with most of the m blocks, with most of these k blocks, then we automatically are getting a good distribution of the d. We are in normality. And because we're doing this in such an explicit way, there are classic estimates for the error in the law of large numbers, and you can strengthen normality for these simply Poisson-generic points. You can find a sequence tending to infinity, so that the distribution of kn blocks in x1, this should be not 2 to the n, but b to the n if we're doing, this was, here I suddenly dropped back to just 2 digits. 10 to the uniform distribution, and here we deal with the variational norm. I mean, this is a refinement that the clock is running, I see, and I do have some more things to say, so I'm going to continue. Now, this notion of simply Poisson-generic is stronger than normality. It's not difficult to see that some normal numbers are not Poisson-generic. Already Champernoun's number, which consists in concatenating the natural numbers written in base B one after the other. And here, the numbers of size b to the k, when you get to write these out, they appear in the region of indices where you're at k b to the k. This is because you're writing them out one after the other, and each one takes k bits. Since consecutive numbers of k digits are almost identical as k blocks, you change the low digits, the digits on the right, you change them very slowly, so there are very long repetitions. When you form the statistics of blocks of length k plus log bk, this is what we should be checking when we're out at kb to the k. We should be checking the logarithm of this number, which is k plus the log of k to base b. We typically see blocks where the initial string of length log bk coincides with the final string of the same length. These are far from being typical, and you see mostly typical blocks, and so this just won't work. You won't see, you'll get something very far from a Poisson distribution. And in fact, you can do more. You can take any normal number and modify it on a zero density sequence. You just have to change n blocks on runs of length, say, twice log n. Put in twice log n consecutive zeros. This is a rare thing for an n block. And given as a normal number, you just change the digits between b to the n and b to the n plus 1 in blocks of size 2n with a periodicity of n over 2. And then you're going to guarantee that any n block has a run of 2 log n consecutive zeros. This is a rare event, but the density of changes is 0, and you've preserved normality, but you've killed this property of being Poisson-generic. So our main theorem is that Lebesgue almost every number is simply Poisson-generic. It's not only simply Poisson-generic, there's a stronger notion, which I'll give in the next slide. One of the puzzles, and 20 years have not enabled us to settle this, is that we don't know of any explicit construction which will give a simply Poisson, even a simply Poisson-generic number. Yeah, you don't see how many slides I have in the format that I've chosen. I have a little more than 20, so we're getting to more or less halfway through, those who are worried about where we are in the lecture. I mean, you don't see the total number. Here are some references. The slides are available. I'm not going to say very much about them. You can check these references. There's lots of work on normality. There's a book on this. This is a broad subject, and we really don't have time to go into a detailed discussion of these things. Yeah, here I made another comment. Here I made another comment which, yeah, okay, I think I leave you this as a kind of exercise to read, and maybe I'll come back to that if we have time at the end. So let me get to the definition of Poisson-generic. So far, I just showed you how you get a single Poisson random variable as a limit. We actually get not just one Poisson random variable, but we get a Poisson point process on the line. So this may be a little less familiar, and the Poisson point process on the line on 0 infinity or on minus infinity infinity, we'll be discussing just on the half line. Intuitively, this is a random distribution of points on the line. To describe this formally, one usually talks about a random integer valued measure, y, on the line. And for any bounded Borel set, the value of y of s is a non-negative integer. This is just counting the number of points in S. If you have disjoint Borel sets, then these random variables are mutually independent. The number of points in disjoint sets are independent. And for each bounded Borel set, y of s has the distribution of a Poisson random variable with a parameter equal to the Lebesgue measure of s. In the formula I gave you before, there was no parameter, it was 1. For the parameter, you have to put in a lambda to the k over k factorial times e to the minus lambda instead of minus 1. Okay, here's what I explained a little more. Now I'm going to explain how we construct not just random variables on our finite probability space, but we're going to use this finite probability space to construct an entire process on the line. And the process that we on the line is if you fix the set S, you scale it with b to the k, and then you count how many times the j in this scaled set is equal to omega. So if S is the unit interval, we're simply counting the j from 1 up to b to the k. If it's the interval from 0 to t, we would be counting b to the k times t. We would be going further. In other words, we count the number of indices such that the pattern appears in the locations. Take a deep breath and swallow this, and now, I've said this already, and this was Poisson-generic. And the new definition is that we say it's Poisson-generic, not simply Poisson-generic, if we have convergence of these point processes to the standard Poisson point process on the line. This convergence in distribution, and I'll soon give you a criterion. I mean, it may not be so clear what you need to do to prove that processes converge, but we'll see that on the next slide. And the main theorem is that for almost every x in the unit interval, these processes defined on these finite probability spaces converge to the standard Poisson process on R. Standard means that the expected number of points in an interval is simply equal to the length of the interval. And to prove the theorem, we're going to use a proposition that goes back to Rényi. Rényi showed that in order to characterize a Poisson point process, point process on the line, to know whether or not it's Poisson, it suffices that it satisfies two properties. One is that the expected number of MKS is bounded by the expected number of the Poisson process. In our case, it would just be the measure of S. And the limit that there are no points in S is just the probability that the Poisson process has no points, which is just, here's the simple example. Under these two conditions, the point, okay, xk should be mk. This x is a typo for m, and when you take for s to be the interval from 0 to t, it's just e to the minus t, which is the probability that a Poisson variable with parameter t is equal to 0. So this is the main condition that one has to check. In the next couple of slides, I'm going to In the next couple of slides, I'm going to give a brief sketch of how to prove the theorem. Theorem is a pointwise result. In statistical mechanics and probability theory, these are called quenched results. And this is to be distinguished from an annealed result where one randomizes the point x as well as the block omega. And the way to prove the theorem is we first prove an annealed version. And here's the lemma that states this. We now use a much bigger measure space. We take product measure on, here I put in z, it should be n, doesn't matter, because the x that we're taking is a one-sided sequence. So on this bigger probability space, the same random variables that we're defining, the same process, converges to a standard Poisson process. And this is the proof of this lemma is more or less standard in, this is a kind of standard thing in probability. I won't be able to describe, to show you the proof of this, but this is not a very difficult result. And now we have to pass from this annealed result to a quenched result. And for this, we use a concentration inequality, which estimates the error from the average behavior. This enables us to apply the usual Borel-Cantelli lemma. So I give here some more details of the proof of the lemma, and let me explain the concentration inequality, because that's a less familiar thing. The concentration inequality is a generalization of what I referred to as Bernstein's inequality before. And it goes like this. The specific one that we need is you have independent random variables, but now you take some function of these random variables. And this function should satisfy the property that if you take two elements which differ in a single coordinate, then the function is bounded by C. This is a kind of Lipschitz condition. And then for any t, the probability that the function differs from its expected value, the probability that this deviates by more than t is an exponential in minus t squared over 2c squared n. So you see how I think there's a typo here as well. The n should be upstairs, not downstairs. Okay. Once you have this kind of concentration inequality, let me go back 2 steps. Once you have this kind of concentration inequality, you know that the probability that we needed to show that this probability is equal to 0 for a finite union of intervals, we need to show that it's converging to e to the minus t. We know that it's doing it if you randomize over x. And so what you need is the deviation from that probability to be an error which is sufficiently small so that you can sum over all k. When you sum over all k, if that sum is finite, you can apply the Borel-Cantelli lemma and get that eventually you are not in the error set and you're converging to the correct thing. So after this brief discussion of I want to pass to a more dynamical point of view. And here I'm changing a little bit gears because I now want to focus on the dynamical aspects of this. So I've already said that looking at the transformation t equals bx mod 1 preserves the Lebesgue measure, one of the classic measure preserving systems, although it's not invertible. In general, a point is called a generic point. Here's the general definition. If you have a mapping of a compact space, you call a point x naught a generic point if the ergodic averages converge to the integral. The transformation t of x equals b times x. This is the usual definition of normal numbers. This explains why we call this Poisson-generic. Now, from the dynamical point of view, dividing into bins or intervals of size b to the minus k is not so natural. It's more natural to divide the unit interval into n equal intervals and look at the orbit up to n. And therefore, we consider the following. For each point x, we fix x as before. Now divide n into intervals of length 1 over n. Omega now represents a random number from 1 to n, instead of a random block up to b to the k. And n sub n super x of omega counts the number of indices I from 1 to n, such that t to the ix is equal, lands in the omega interval. Now, if you consider omega to be uniformly distributed on the integers from 1 to n, this becomes a random variable. Our previous mnx was just this, but using b to the n. And in a similar way, you can define a point process. You just scale the n up to t, and you just count the number of times up to n times t that the orbit lands in this transformation. Now, t to the I is just b to the I. We're just using the definition, I'm just using the notation now. I'm just using this notation. T of x is b times x. So with this, we now have a new theorem. For almost every x, we have that this converges to the standard Poisson process. And this is a generalization of the previous theorem, because if you look at the times b to the k, then this is the previous definition. And here's the annealed version, and the proof goes through the same the same mantra as the proof I was describing before. Now, why did I put this suddenly into a dynamical setting? I put this in a dynamical setting because this suggests that instead of multiplication by b, we can use other mappings. And I think this is the more interesting novelty in our work. And the next simplest example, you might disagree with this, but I'm thinking of the next simplest example of a hyperbolic system. The simplest example of a measure-preserving transformation is probably rotation by alpha on the circle. But if you want to get some randomness, you really need to go to the torus if you want an invertible transformation. And the simplest example is an ergodic automorphism of the torus. This is given by an element of SL2Z. This is just a 2x2 integer valued matrix with determinant 1 with eigenvalues that are not roots of unity. You need this in order to ensure that the eigenvalues, you have hyperbolic behavior. Otherwise, you have some periodicity. It's not an interesting transformation. Denote by A such an automorphism. You can think of the simplest matrix that you like. 2, 1, 1, 1, for example, is probably the simplest one. And now fix a point on the torus, on the two torus. For each n, divide the torus into n squared equal size squares. So this is just a checkerboard pattern. Now, omega denotes one of these squares chosen uniformly. Now we define a process just like we were doing before. X is the fixed point, n is the length of the orbit, t is the parameter for the process, and when you evaluate it on this finite probability space, which now has n squared elements, it's the number of indices between L and n squared such that a to the Lx is in omega. So the probability, this is measure preserving, the probability that you land in any square at any given time is exactly 1 over n squared. So the expected number of times you land in a given square is 1. So we now have something which we're sort of summing, we're summing not independent, but we're summing n square variables, each of them with probability 1 over n squared. We expect that the sum behaves like a Poisson random variable. And as expected, for almost every point, we can prove that these processes converge to the standard Poisson process on the line. Now, this is already going, I think, beyond this strengthening of normality that I was emphasizing in the first part of the talk. I'm supposed to remember, yeah, 1220. Okay. So there are many papers with Poisson limit laws for dynamical systems. These usually concentrate on distribution of return times or visit times of a randomly chosen point to a sequence of sets that shrink down to a fixed point. Here, the basic sample space is the whole torus rather than the finite set of n squared. These are maybe not so familiar, and so among the first paper of these type was a paper by Boris Pitzkel. It was actually published after he passed away. He passed away tragically at a young age. And a special case of his result I'm going to formulate here. Let A be a hyperbolic toral automorphism. That means that the eigenvalues are not on the unit circle. So for the two torus, it just means that you have to avoid roots of unity. You fix a point in the torus, y, and then you let Bn of y denote the ball of radius r to the n around y. R is less than 1. You take some fixed radius and you start shrinking this. And now, with this fixed point that you've chosen, x, you look at the number of times that your orbit, ai to the x, lands in the ball of radius r to the n around y. And the time that you go is you take a lambda as a parameter and you divide by the measure of the set. M denotes the Lebesgue measure. If x is M distributed, for M almost every y, and M almost every x, I should have said that as well. I'm sorry, x is M distributed. For M almost every y is fixed, and x is the random point. My x converges in distribution to a Poisson variable with parameter lambda. So this is the, so the y is fixed and the sample space is the whole torus. So this is a kind of annealed version. Now, I didn't formulate Pittskel's real theorem. His real theorem was for finite state Markov chains. And he proved the same kind of result for finite state Markov chains. There you don't use simply blocks because blocks don't have equal sizes. You use sets that are roughly equal that are defined by blocks of roughly equal length. And then to go from the Markov chain theorem to the theorem on hyperbolic toral automorphisms, he used the fact that there are geometric Markov partitions for hyperbolic toral automorphisms. These are partitions of the torus into piecewise polygons, piecewise rectangles. And these Markov partitions are used to show that the algebraic toral automorphism is isomorphic to a Markov chain. So it behaves measure theoretically just like the Markov chain that you get from this representation. So you prove the result for Markov chains, then use Markov partitions and approximate the squares, these balls, you approximate them with sets in the Markov chain, and with that you prove the Pittskel's theorem. This gives a kind of annealed version of what I was claiming on the previous slide. I mean, it's not exactly that setting, but it's similar enough. Let's see what happened. What happened here? I went backwards. Yes, I should be going forward. Is Pittskel's theorem. Okay, I've gotten to the final remarks. Okay. Is this what I wanted to do? Excuse me for a second. Yeah. Okay. I do have another slide. Yeah, okay. I see. So, there are properties of the class of normal numbers that do not seem to be shared by the class of Poisson-generic points. The simplest is the following. So I'm going back to discussing the connection between Poisson-generic points and normal numbers. If from a normal number you get a new one by erasing all the digits with an odd index and then contracting, so you just look at the even digits, the new number is also normal. You do this the same with a Poisson-generic point, it's not at all clear that the resulting point is again Poisson-generic. Because now we've cut down by a half the length, so we should be looking at distribution of, we're looking at every other, so these are blocks of length 2n minus 1, that we've taken every other one, and we're looking at this up to 2n, and it's not clear at all that this carries over, that you do this sampling and you get another Poisson-generic point. The proof I was sketching that Poisson-generic implies normality carries over to the dynamical setting that I was describing in the previous slide on the torus, with the same kind of proof. There's nothing really needs to be added there. I've been talking this whole talk about the Poisson limit theorem. The central limit theorem is probably better known than the Poisson limit theorem. There are also pointwise versions of this. These are called, you take identically distributed random variables with zero mean, variance 1, you normalize the sum by 1 over square root j, so you're now looking at the deviation. You expect this to be 0, and you're looking at the deviation on the scale of root j. You fix a realization of the sequence, and you take the integers from 1 to n as your sample space, but you sample with a proportion over j, so you're taking really what is called a logarithmic average. Then the almost sure central limit theorem is the assertion that z omega n converges to the standard Gaussian. So this is, I point this out just so that you know there are other, from almost every point you can also get in some natural way Gaussian random variables. And there are pointwise Poisson limit theorems of the same type, which are similar to the theorem of Pitskill that I was describing. Here you can, he was taking he disconnected the point x from the point y. The point he was using to, you can use the same point and just look at the return times of an initial n block in a fixed sequence. And this converges, this has a normal Poisson limit theorem, anneal for almost every block. The probability when you do this over blocks is similar to the theorem of Pitskill that I was describing. In these cases, I don't see how to show that a point which satisfies them is a normal number. There's another typo. Okay, I think that I have about a minute left, and I will conclude here. I don't have a slide saying thank you to everybody, but I say thank you to everybody. And I see that Robert has returned.
Yes, so thank you for your talk. I hurried up to be in time at the end of your lecture. And of course, I could hear your comments on normal numbers, which was, of course, for me of interest. So thank you very, very much. And I see also that there is a list of questions already in the chat.
Okay.
So I can read them. Do you see it, or?
Wait, before that, I should have said at some point that one of the papers, I think, that I was mentioning, Robert should know, because I think he wrote the math review of that paper.
Yeah, that's true.
Okay, so now I see questions. Okay.
Yes, of Barak, he asks whether...
Wait,
you can read it.
There are a whole bunch of questions.
Yeah, other measures. He asks, instead of Lebesgue, what about other measures instead of Lebesgue measure?
Instead of Lebesgue measure. So in principle, if you use for almost every point have a base 2 expansion, which is Poisson-generic. Oh, okay, this is a much, much subtler problem. It's already a subtle question. It's already a subtle question for normality. I mean, this is something we haven't investigated at all. I have no idea offhand.
Okay. Then a bunch of comments by Veronica Pescher.
Okay. So the subsequence along squares of 2 and more is normal. Our experimental results show that this subsequence could also be Poisson-generic. Beautiful. I would be extremely interested in normality of the subsequence was proved by Milner for a larger class. It could also be Poisson-generic.
Yeah, this is concerned with these automatic sequences.
Yeah. I know. I mean, the 2 or more I'm of course familiar with. I would be offhand. I mean, I can't. I'm happy to see these comments. I assume you learned about Poisson-generic from some references in some papers of Kamaya, but definition can be given with overlapping occurrences as with non-overlapping. Does the same hold for the Poisson-generic definition? We use the overlapping condition. In other words, we're counting occurrences. We're not asking whether or not the I don't know. I don't think there would be much difference. But I really don't know. I see Zeeb sent me a private communication. How do I see that?
Yeah, maybe this is an answer to your comment that she got the information from Kamae, and maybe she says...
by Zeeb Rudnik.
Yes.
Okay. She heard it from Zeeb. Very good. Okay, thank you.
Yeah, are there further questions, comments? See the next one.
Excuse me? Exactly, yes, okay.
Exactly. No, there is a further one.
Okay.
Should appear sometime.
Yeah, okay. She's typing.
Huh?
Is there some way I can see her when she's asking these questions, or is that...
Maybe I can, maybe our technical administrator in the background can manage it, yes?
Yeah. Can we get the paper with these results? You'll be the first to get the paper after we get the paper. So wait
a moment, I try to make Veronica visible, but maybe that's not possible. I don't know.
Yeah. In any event, Veronica,
you can see her.
No. Now I see her. Very good. Okay. I'll be happy to put you first on the list once we get the paper written. So far, 20 years have passed. I hope that it won't be another 20 years. But at the moment, we don't have a real manuscript. I mean, we've discussed this, spoken about it, and so on, but I'll convey to my co-worker your request in hope that this will encourage us to write down finally these results. Okay. Although there are some hints, I mean, there is I think the paper of Kamaya that I refer to, that I mentioned, I think that he gives some idea as to what our proofs are, because he says that he uses some of our ideas to prove what he's doing in that paper. So if you haven't looked at Kamaya's papers, I would suggest you look there. I hope I've given more hints in the talk, and it's really not so difficult. It's not.
Okay, so Veronica, do you have other questions?
No, we don't hear you. You're muted. Veronica,
Yeah.
we don't hear you. You have to unmute.
I don't have more questions at the moment. I will be pleased to send you the statistics on the examples we tried.
Oh, wonderful, wonderful. Yeah, please do.
Okay, so thank you very much. And
okay.